Thanks, Paul. Yeah, thank you for having me. I'm in week number 3, and I'm going to talk about, when I get to the results sections, collisions between photons and particles. And I learned about collisions when my older brother, who came here to Monash, did his degrees here, and he taught me snooker. So I played a lot of snooker over here on campus. I was still in high school at the time. Okay, so I'm going to talk about oh, I did. This is not the title of my. I changed my. I didn't update the title. Anyway, the title that's on there is the official. Doesn't matter. These are magnetar mysteries that I'm going to talk about. The magnetar field has undergone a transformation in the last 6 years due to a lot of electromagnetic observations, and I'm going to focus on the electromagnetic signals today, and specifically X-rays from their surfaces. Okay, I'm going to give you a long introduction so that you sort of have the background for what neutron star astrophysics looks like, and the focus on the background for magnetars. I have a bunch of collaborators. I have a couple of former PhD students, Joe Barkas and Kun Hu, whose work forms the basis of the simulation that I'm going to show results from, and a current postdoc, Hoadin T, who has upgraded it and polished it and generated a number of the results that I will show today. I have my observational collaborators, George Eunice and his PhD student, Ray Stewart, and other collaborators in the broader scheme of things, where we do lots of different work on magnetars. Okay, so first of all, magnetars are neutron stars, and neutron stars are end states of main sequence stellar evolution. You blow up a star probably around between 6 and 15, 12 to 15 solar masses. Its core collapses. It produces a compact remnant that is maybe the same mass as a white dwarf star, but it has too much gravitational energy density in its collapse, so that it produces a much more compact object, primarily composed of, we believe, neutrons. Okay, we don't know that for 100% sure, but that seems to be what physics would dictate. Physics that we first understood in the 1930s, because neutron stars were predicted by Barnett and Zwicky in 1934. Okay, as a natural consequence of using high energy density in the environment of a deep gravitational potential well to drive neutronization equilibrium towards producing neutrons. In other words, you're tapping the energy that you've got from your pressure system that has to support the star. Okay, so neutron stars are not very big. Here's it is drawn over Manhattan. Okay, so it would be out to maybe Swinburne from the center of the city, maybe a little bit further, but not out this far. They're too small if you were to center it on the CBD. Okay, so they're about 10 kilometers across. Okay, so the structure of a neutron star, as more or less a standard model, is very complex, and it's very difficult to know exactly what the interior is, because it's very difficult to probe the interior. The best probes we possibly can have are neutrinos, but the neutron stars are too far away on average for us to see steady neutrino signals from them. So we need one very close by, and if it were close by, it would be dangerous to us, because these X-rays would then irradiate us at levels that would be damaging to our atmosphere. So the outer layers, which is what I'm going to focus on here in this talk, is the surface. It may be hydrogen helium plasma. We don't know for sure. It may be pure iron nuclei or exotic heavy nuclei. We don't know for sure. We have, and part of the problem is that we don't have lines, absorption lines, like we have in standard stellar, standard stars, main sequence stars that emit in the optical. We need them they would be in the X-rays, and we would see absorption lines corresponding to K-shell type activity in iron. We see these in other astrophysical systems, usually as emission lines around accretion disks. And we see oxygen, we see magnesium, etc., in those systems. But in neutron stars, we don't see them. Okay, so we can't do direct compositional diagnostics on the surface, but we think that this is a reasonable abundance conjecture, if you like. Then we go to a region called the outer crust, which is going to be mostly heavy ions, and those ions are exotic ions. They're not the stuff that we produce in our labs. They are beyond what we can produce in our labs. Usually they may have mass numbers anywhere between 80 to thousands. Let's put it that way. By that stage, they're so heavily neutronized, they're ephemeral species. Then we go to the inner crust, and basically we've got the heavy ions are then morphing over into, breaking up into basically neutrons. We're basically colliding electrons with any protons in their heavy ions and converting them to neutrons. We have relativistic electron gas, and it's in some sort of soup, except that the ions can still form a structural lattice. Okay, they have sufficient binding energy that they can form the lattice. When we go further into the outer core, basically the energy density is so high, the pressure, which is the energy per unit volume, is so high that it disrupts the lattice. It dissolves it, and you then just start to go into a fluid. And then you can have predominantly neutrons, you will have some protons, you'll have electrons, then you will start to pick up more massive species and more exotic species in the standard model of particle physics, muons. And then you can go on, you can get hyperons, deltas, and bosons right in the inner core. You could get quark gluon plasma, some sort of condensate. You may have superconducting matter, boson condensates. We really don't know. The way to probe this interior as best we can is to have a model that builds some picture for the interior, builds a self-consistent structure, including general relativity, and then form the mass and the radius of the star, and then try and probe the mass and the radius using surface X-ray diagnostics. It's a difficult game. Okay, so there are exotic states in the outer crust, etc., near the surface, where the strong magnetic field that is embedded in the surface layers of a neutron star basically sort of streams the matter in sort of one-dimensional configurations. Okay, so we'll get to the magnetic field. So those were modern ideas of neutron stars. The principal ideas of neutron stars from the 1930s, when we had early incipient nuclear theory, were very primitive. It took until 1967 to get a discovery. That discovery was at Cambridge in radio by Jocelyn Bella and her PhD supervisor, Tony Hewish. And they discovered this pulsar B1919, which is its telephone number in its direction in the sky, which means it's not at the galactic center, but it's somewhat towards the galactic center. Okay, and it's sort of like they localize the position, and you sort of see this blip. This is the train, so it's sort of blipping along. So it's like a little periodic signal. Okay, and then they started discovering more of them in the late 1967, and then the famous ones, the Crab pulsar and the Vela pulsar, were discovered in 1968, and the field took off. When I left Melbourne to start my PhD in the mid 1980s, we had 500 pulsars known. Nearly all of them radio, and 2 of them in gamma ray, some in X-ray. Okay, we now have well over 3,000, and we have over 300 in gamma ray. Sorry, over 200 in gamma ray. Okay, so the model that you have, the picture is it's that this blipping is due to rotation. The radio is a very sort of collimated, narrow beam over the magnetic pole. So you have a neutron star sitting here, and it has a magnetic field. Why does it have a magnetic field? If you take a mean sequence star, it has a magnetic field. The sun has 1 Gauss, or 10 to the minus 4 Tesla, is its mean magnetic field, higher in sunspots. You take that field and you say, I'm going to blow up that star, and then you use flux conservation during the evolution of that core, during its collapse, once you get that supernova remnant, going off. With that core collapse, you're reducing its surface area by 10 orders of magnitude, ballpark, maybe 11 orders of magnitude, and that means your magnetic field has to go up by 11 orders of magnitude during the collapse. So you know you're going to get about 10 to the 11 Gauss. If you take a more massive star, it tends to have a higher magnetic field in its progenitor phase as a main sequence star, and so you're likely to get about 10 to the 12 Gauss. That's what you'll get. Those will be the currents. Basically, you're taking currents and you're shrinking them into smaller volumes. They move faster, they're moving relativistically instead of non-relativistically. The densities go way up, the charge densities, so your magnetic field goes up. So that produces a magnetic field, and that magnetic field moves plasma around it, and in the region that's connected to the star, which we call the closed magnetosphere, the plasma can exist for long times, and it can sustain departures from an idealized morphology of the magnetic field. We usually use this idealized morphology, a dipole. It's a spinning bar magnet. It's anchored, the bar magnet, the currents predominantly are in the surface of the star, but there are also currents in the magnetosphere. We have this arbitrary mathematical surface, not arbitrary, but idealized mathematical surface we call the light cylinder, which is the position, the cylinder, at which the co-rotation speed, if the field lines rigidly rotate, then they're moving at the speed of light c. So that's idealized. In practice, those field lines have to be distorted and dragged out, and they get swept back so that they are causally connected, okay, so that it actually solves Maxwell's equations. So this, you can't have rigid co-rotation, but it's a good approximation down near the surface of the star. What we find is, so this is the radio beam is very collimated. We also find X-ray emission and gamma ray emission. The X-ray emission, the low energy, which we call soft X-rays, below typically around 5 keV in photon energy, are all at the surface. Above that, they tend to be a mixture, and we get a lot from the magnetosphere. The gamma rays all come from the magnetosphere. They can't come from the surface because they get absorbed and reprocessed down to X-ray temperatures. Okay, so that's the global picture. So you've got a rotation axis, and the magnetic axis anchors the radio beam. So the radio beam is actually coherent emission that is still not understood. Its origin. It may be some maser-type mechanism. It's an enigma, and it's been well studied for 50 years. And we still don't know exactly what it is. It's highly polarized, and it sweeps as the star rotates around its rotation axis. Because its magnetic axis is tilted, then the beam can sweep across our line of sight, and that's what causes the pulsation. Okay, that's true of any other band. And pulsation is central to this talk. Okay, so we have over 3,000 radio pulsars, many of them with what we call good timing and measured period changes. And that's important because that gives us a path to measuring their magnetic field and their age. The radio band is the most sensitive one, but it's not the most luminous one. The most luminous one is in gamma rays. So we have over 300 gamma ray pulsars discovered by NASA's Fermi mission, specifically its Large Area Telescope, LAT. Okay, that is where the power is. We also have about just over 60 isolated and binary X-ray pulsars. We have 30 optical pulsars. We'd like to have a neutrino pulsar, but like I said, they're too far away. The focus of this talk is a separate category called magnetars, and we have about 30 of those. Okay, so that's the census. If you want to look at them where they are in the sky, here is a image of where all the pulsars are as of 2023 in the third Fermi pulsar catalog. And the coordinates here, this is an ATOF projection, and these are galactic coordinates. So the galactic plane is along here, and the galactic latitude is in this direction, denoted B. The longitude's around here, and the galactic center is here. And then there's all these different colors, okay? The only thing to note is that we can divide up all the ones that, since this was a gamma ray pulsar catalog, the red triangles, the orange triangles, the red triangles, the blue squares, and the green dots are all gamma ray pulsars, and everything else that's black is a radio pulsar that's not a gamma ray pulsar. And so what you see is a clustering near the galactic plane, but you also see a broad distribution in galactic latitudes. And a lot of those pulsars are actually millisecond pulsars at high galactic latitudes associated with globular clusters, which means that they're old. Billions of years old. Okay, so now let's go to magnetic fields. So we have a neutron star, and it's a ball of currents, at least in its outer layers, and its bar magnet is inclined to a rotation axis, and so it's spinning around at a bar magnet, and this is a classic problem in electromagnetism, is to solve Maxwell's equation to determine that you actually have an electromagnetic torque on your bar magnet because it's tilted with respect to the rotation axis. What that translates to is if you pick any point in space, you obviously see I'm going to have a dB/dt, a time rate of change of magnetic field. Because you're solving, when you solve Maxwell's equations, you have your dB/dt, you're going to have an electric field. You turn out to have because there's a local rotation velocity, and so you have a V cross B effective electric field, that is also time changing. So you have a dEdt. That means that you have a solution to this problem where you have linear waves propagating energy. It has to go out, is essentially a thermodynamic principle. So it goes out to infinity. So you're taking energy from the system and sending it to infinity in the form of a coherent electromagnetic wave at the rotational frequency of the pulsar, which turns out to be a frequency that's so slow, read 30 hertz, read 1 hertz, read zero point 0.2 hertz, that is absorbed by the ionosphere of the Earth. So we can never detect it here on Earth. On the moon, maybe different. Okay, so we're taking energy, we're taking also angular momentum, and if we're taking that out of the system and the origin, the principal source of energy, the best reservoir of energy is the rotational kinetic energy. So we extract rotational kinetic energy through this electromagnetic torque and send it to infinity. For young pulsars, if they're oblate and if they're spinning really fast, they may be born with millisecond periods, which means they have 200, 300, 500 hertz rotational frequencies. If they're oblate, they have a quadrupole mass moment, and that means that they are going to radiate gravitational radiation, and they're going to send that to infinity. And we believe that for very young pulsars, the dominant source of torque is actually a gravitational torque, and that's what causes the rotational kinetic energy to drop at very early ages. The transition stage is about 100 to 300 years, is what we believe. Okay, so now we can go into a little bit of the mathematics. So again, we have a rotation axis with a rotational frequency of omega, which is 2 pi over the period of the pulsar. The magnetic field axis, which we denote here by B, is tilted at an angle of alpha. And we want to know what alpha is, okay, for what's going to become obvious from this. Okay, so if we solve our electromagnetic equations, Maxwell's equations, we can calculate the rate at which energy is lost due to the electromagnetic torque. And it's proportional to the square of the magnitude of the magnetic field, which is down at the surface pole of the neutron star. And that's what we call B0. It's proportional to the square of sine alpha, where alpha is that inclination angle. So if alpha equals 0 and the magnetic field is aligned, at any point in space, you have no dBdt, no dEdt, and you have no coherent electromagnetic radiation. It's proportional to the fourth power of the rotational frequency. In other words, inversely proportional to the fourth power of the period. Okay, so you have a magnetic moment squared appearing in that formula. We equate that to the time rate of change of the rotational kinetic energy, and the rotational kinetic energy is half the moment of inertia I times the square of omega. So with that, we have a differential equation in omega. Omega dot is proportional to omega over omega to the 3. We can solve that equation, and we can get a solution, find the time solution, and we find that the angular frequency drops as 1 over the square root of time, and that the period increases as the square root of time for late times, large times, in other words, long after the birth of the neutron star, of the pulsar. The coefficient depends on all of these pieces of information, so the coefficient says that we can find and estimate a value of B0 by inverting this relation and the solution. Given a moment of inertia, which is around 10 to the 45 grams centimeters squared, speed of light, the radius of the star, which is around 10 to the 6 centimeters, if we can measure the period and the time rate of change of the period, which we call P dot, dPdt, we can estimate the magnetic field at the surface of the neutron star, of the pulsar. We can also estimate from the same solution of this equation, which I won't go through the mathematics, that the average age, the characteristic age of the neutron star as inferred for a particular period and period derivative is just the ratio of those two with a factor of 2. So this tells us, and then we can go and compare a particular pulsar if we have a supernova remnant and some sort of age estimate of the supernova remnant. In the case of the Crab pulsar, we have a historic supernova in 1054 AD observed by the Chinese, and we find that this estimate is pretty good. It's inaccurate to about 20 to 30%, but it's still pretty good. Okay, you get a number about 1,000 years, and it's about 1,000 years. Okay, it depends on how you do this. Okay, so this is how we infer magnetic fields. So this then leads us to the what we call in the field the pulsar astronomers Hertzsprung-Russell diagram, which the Hertzsprung-Russell diagram is the classic diagram from main sequence stars and stellar evolution theory. But here we have an x-axis of the period and the y-axis of the period derivative, or p dot. And p dot is the PDT, so it's dimensionless. The periods in seconds and both scales are logarithmic. So the period is between a millisecond here to a second to 10 seconds and a little bit beyond. The period derivatives starts at 10 to the minus 22 or around 10 to the minus 21, goes all the way up to 10 to the minus 10. So 10 to the minus 10 means you're changing the period by 1 part in 10 to the 10 at any given time. Okay, so over the period of a year, which is 3 times 10 to the 7 seconds, you've changed the period by about 1/300th of a second. Okay, so that means you need a very precise clock to measure periods. Down here, you're looking at not 1 part in 10 to the 10, but 1 part in 10 to the 20. So you're changing the period by something like 3 times 10 to the minus 12 seconds in a year. Okay, that's pretty darn small. So then we have distributed all the pulsars. This is an old diagram. This dates from 2013. So it doesn't have all the pulsars on it, but it gives the same message. All the black dots are radio pulsars that are not gamma ray pulsars. The purple triangles, those are gamma ray pulsars. And these ones up here are called young gamma ray pulsars. These ones down here are millisecond pulsars because their periods are a few milliseconds. There's a millisecond there. On this diagram, we draw lines of constant age, which is P over P dot equals a constant. That's 1,000 years, 100,000 years up there, 10 million years, a billion years. So this gives you the sort of a generic placement of any pulsar of how old it is based on its spin history or its estimated spin history, what it's doing now and what we think it would have done in the past. So a pulsar, as it ages, drifts across this diagram like this. Okay, the reason I say it drifts across that because I'm making the assumption that it doesn't change its magnetic field, and that's magnetic field decay is a separate discussion. We can have that taken care of that at question time. But if its magnetic field doesn't decay during its nominal lifetime where we're able to observe it, then it just slides across this diagram parallel to these lines, which are lines of constant P times P dot. And here's one drawn for 10 to the 13 Gauss. Here's one drawn for 10 to the 9 Gauss. So that's 10 to the 5 Tesla, 10 to the 9 Tesla. So these ones are about the magnetic fields of the most magnetic field white dwarfs. That's what millisecond pulsars are. These fields are the field strengths of a crab-like pulsar, which sits right there. And most pulsars, radio pulsars, are in the 10 to the 12 to 10 to the 13 Gauss. Up here, in the upper right, with periods generally above 1 second, about 2 seconds, and up to about 12 seconds, are the red squares, and their fields are 10 to the 14 and 10 to the 15 Gauss. Okay, so these are nutcase fields. They are nutcase fields because those are where exotic quantum effects, the first really discussed in the 1950s and then in the 1960s, could in principle take place. And we're going to talk about one of those. These red squares are magnetars. They're the most magnetic neutron stars, and they are weird compared with average pulsars. So this is how we estimate magnetic fields. Obviously, the best way to get a confirmation of a magnetic field is to look for a cyclotron line because the energy of the cyclotron line is proportional to the strength of the magnetic field. And we're able to do that in a select subset of a handful of X-ray binary accreting X-ray neutron stars accreting from a companion star where we can actually see a cyclotron line, absorption line in hard X-rays. We're not able to do that with magnetars and most pulsars. Okay, last thing on magnetars is that lots of their activity is associated with not steady pulsation. They have their steady pulsation. We see them in X-rays and we see them pulsing, and that's what the focus of this talk is going to be about. But we don't often detect them that way. We don't find them that way. We find them because they are exotic. They are producing a lot of transient energy in their magnetospheres. And how that manifests itself is what's called bursts, which are very short-lived, typically that they're chaotic light curves. These are counts versus time, and this is a range of about 1 second here. And so they have this spiky structure, and this is the number of counts, and we see them at energies between a few keV all the way up to about 200 keV. And this is the spectrum drawn there, seen with two instruments, and it's actually the spectrum multiplied by the square of the photon energy. So the differential spectrum's tilted like this. This representation of the spectrum says that most of the energy is up here, around 50 to 100 keV. So these live for very short times. However, they have a lot of energy. Their luminosity is typically around about 10 to the 39 to 10 to the 41 Hertz per second, which puts it at 6 to 8 times orders of magnitude larger for this short period of time than the optical luminosity from the sun. So we look in space with hard X-ray telescopes tuned to these bands and then say, oh, wait a minute, I'm seeing something popping off, a little bright transient. Go have a look. And then we can pin down the magnetic field strength by looking at the steady emission and finding by measuring the period and the period derivative, finding that the object that's producing those bursts lives up here in the PP dot diagram. Okay, the rest of the talk is about persistent surface soft X-ray emission. And that means this stuff. So when you look at a broad spectrum of a magnetar that, such as 2259, which is producing radiation all the time. So we go look at with different telescopes and we can see it. Here we have the spectrum log scale energy in keV. So that's 1 keV, 10 keV. We have, again, this multiplying the spectrum by the square of the photon energy. So those, it's also in log scale. So those are decades there. And this is saying that most of the energy along, which is the highest part of the y-axis, is where the most of the energy is. This emission looks like a black body. And so it's thermal emission. And we believe that's all coming from the surface. And that's pulsed. This piece and this piece are quasi-power law components. They are above just an extension of a Planck spectrum, and we believe that they have to come from the magnetosphere. The pulsation looks like this. Okay, these were done with different instruments. That was done with Chandra. This was done with RXTE, which is this mission. And you sort of see as a function of pulse phase. So a period is, there are two periods shown here, and this is time along here, which we denote as pulse phase, fractional time. And so that's going from one period to the next. And you sort of see a peak in the number of counts on the y-axis. This is a linear scale. And then it drops down and it rises again. And there's a little bit of structure there. The structure is secondary, but it's still important. As you go to higher energies, this is at low energies, below 4 keV. This is above 4 keV. That secondary peak increases. And that's what this component is all about. So if you want to look at the surface, you want to look at this peak, you want to limit yourself to less than about 4 keV in energy so that you're just probing this information here. If you start to probe information about the magnetosphere, its geometry is different from the surface. So it's giving you different clues. They're complementary clues, but they can also be confusing ones. So we have to isolate. So this is all about intensity, how much light per unit time. We now have, as of four and a third years ago, a new X-ray polarimeter, the first one we've ever had, that is a dedicated polarimeter called IXPE, the Imaging X-ray Polarimetry Explorer, launched by NASA just over 4 years ago, and it has been able to detect 6 magnetars and measure polarization for them. Okay, I'm going to show you some of those results. Okay, so now let's go and look at the questions. So in that PP dot diagram, the derivation up there, we found that we can measure the magnetic field modulo this sine squared alpha factor. Okay, so we've got a P and a P dot, and there's, in that algebra, there's a sine squared alpha. If the sine squared alpha is small, or if it's near 1, that gives us a large change in the range of our estimate of the strength of the magnetic field. So if we know what that angle is between the magnetic moment axis and the spin axis, we can pin that down. Then that's helpful. That's very helpful. So that's one of the key geometry parameters for a spinning neutron star, in this case, a magnetar. The other one is where our telescope is relative to the rotation axis. And that's a different angle, which we call zeta. So zeta is the angle between our line of sight direction to the center of the neutron star and the spin axis direction. So the green denote the curved trajectories of photons in a general relativistic spacetime. We're going to look at the soft X-ray emission, which comes from some surface patch, probably around the magnetic pole. The reason we think it's around the magnetic pole predominantly is because there the field lines are vertical, and that means thermal heat conductivity is coming up from the surface. I'm going to get that in a minute. Very effectively, because in a strong magnetic field, these super strong magnetic fields, thermal conductivity across magnetic fields is heavily suppressed. It's easy to conduct heat up and therefore heat the polar caps. Okay, yes, question?
These three axes don't have to be even in the same plane. So here they're drawn all in the same plane, but in principle they could.
Okay. You'll see a slide where I'm going to pull you off that plane. Okay. Later on. So yes, the answer is yes. Yes, they don't have to be in the same plane. Okay. So as the star, so you could have a second one, and I'm going to show you some results where we have a second hotspot down here. You could actually have them pushed off, having them asymmetric, not antipodal. You could do that. And we have some evidence where that might actually be the case. As the neutron star spins, this hotspot, it sweeps around. So just as in the radio cone, so the radio cone, I'll not do it with my laser. The radio cone is a narrow cone. So it's pointing like this, and you're the observer. And if I'm sweeping it like this, it glances with some of you, and most of you miss it. If that radio, so that's a radio cone that's narrow. Your X-rays is largely a broader cone, so it's a larger angle, and I can do the same thing. If it's oriented on the magnetic axis over here, then it will sort of follow the radio and be aligned with the radio, but you'll see it more often, and you'll see a broader light curve, a pulse profile. So the larger the surface, the angle, the solid angle of emission for any component, the broader this pulse peak is. Okay, so we're going to see what the difference between radio and X-ray looks like. Okay, so, and then we have the magnetic field. At the magnetic pole, the magnetic field is vertical, but when you start to go to significant magnetic colatitudes away from the magnetic pole towards the equator, the magnetic field is tilted. So you have to model the details of this with precision and complexity with numerical codes. We can solve it with radiative transfer, but it's very difficult to do in these complicated magnetic geometries. So we have a Monte Carlo code. We call it MAGTHOMSCATT. And what it's doing is taking a piece of that blue patch, a very localized piece, and we inject photons deeper down in the atmosphere, and we follow the radiative transport. We follow them scattering around. It's the dominant mode of the dominant cross-section in the outer layers is due to scattering, just Thomson scattering. Okay, so that's what's modeled here. You actually see the diffusion of photons with these trajectories. This came straight out of the simulation. We have some scale height for it, which we actually list in optical depths. The magnetic field is generally not vertical along the zenith direction, but it's tilted. And towards the equator, it's really tilted. And we can follow the radiative transport in any magnetic field configuration. So this gives us a localized region, which may be here. And when we go somewhere else, we can do a different simulation, and then we record this data. We send all of the photons that we inject, typically somewhere between 100 million and a billion, and send them out to infinity. They go out, they follow curved trajectories, these green lines. And so we actually do everything in the Schwarzschild metric. And the reason we use that is because magnetars are slow rotators with periods of 1 to 12 seconds typically. And that means that the frame dragging effects that occur in the Kerr metric are minimal. They don't influence the propagation to infinity. Okay, so this is the basis of the simulation in terms of the geometry. So it's a thick slab, and then basically you're looking as you go further and further away, you're sort of bending the slab, but that's always local. It's a very thin slab. We're talking typically a centimeter or less is what it is physically. Okay, the physics that's in the scattering is different from what you're used to seeing. What you're used to seeing is this horizontal line here. So what I've plotted is the log of the photon frequency divided by the cyclotron frequency, or the photon energy divided by the cyclotron energy. And so when that equals zero, that log equals zero, you're at the cyclotron energy. So what you're used to seeing, and then on the y-axis is the log of the cross-section divided by the classic Thomson cross-section, 6.6 times 10 to the minus 25 centimeters squared. That's log scale too. So that's six orders of magnitude there in cross-section. So that's what I plotted. And the Thomson cross-section, of course, is independent of the energy. And if you were to go to very high energies, you would have to correct for it. And you introduce QED effects. And so you would get recoil in your scattering, and you would get a reduction, a Klein-Machine reduction in your cross-section. Okay, and that would fall off. So that's what we use in lots of astrophysics calculations. Now, here we have a very strong magnetic field. And what that does is introduce this resonance at the cyclotron energy. And so the cross-section rises. How much it rises depends on what the polarization of the photon is. There are two polarizations plotted here. One is parallel, which is called the ordinary mode, O mode. And that's one, depending on the photon angle with respect to the magnetic field. If it's perpendicular, it's just this horizontal Thomson cross-section. If it's along the magnetic field, it rises like that and then drops off. If the polarization mode is called the X mode or perpendicular mode, where the electric field vector is perpendicular to the plane defined by the propagation direction and the magnetic field direction, then the cross-section rises like this and you just have a resonance. So you have high angular dependence on the cross-section and high polarization dependence on the cross-section. And that is the reason you want to have a Monte Carlo simulation to simulate the radiative transport, because you capture all the intricacies associated with anisotropy and how it connects to the magnetic field direction through the slab. Okay, so this is a very prominent resonance, 3 orders of magnitude, say, above the Thomson cross-section. So this tells you that there's going to be strong influences on the escape of photons. Same when it's very much below. This is actually a classical calculation. It was first done in 1971. For this, the non-relativistic quantum theory calculation for this is identical. It gives the identical result, first done in 1979 by Heinz Herald. Okay, so then when you go into QED, you get a lot more resonances, harmonic structure, and the cross-section falls off with all the Klein-Machine effects, and that's a real mess. And we are not yet, we're still working on that in terms of honing the cross-section in order to be palatable for porting in to a simulation. For the magnetars, it turns out that the cyclotron frequency, the electron cyclotron frequency, is so high, the energy is in the MeV band, and we're looking at soft X-rays around a few keV. So this is actually a really good, it's really accurate. Okay, so now we need to get to results. I'm going to skip over that because the time is zinging by. And I'm going to say, okay, so now let's get our blue spot and we're going to sweep it around. So you look at a particular pulse phase, which is, say here, somewhere a cut on the x-axis. And we're just doing the top row here is the intensity. And so we just take a slice there. You make a measurement of intensity. Now, somebody over here will make a measurement of intensity. Somewhere over here will make, at the same time, a different measurement of intensity. But the neutron star is rotating. So when it rotates over, at a later time, people over here may measure the same intensity as people over here measured earlier. So this is all encoded in the behavior of intensity, which is in the y-axis linear scale, versus pulse phase or time in units of periods, 1 period, 2 periods, on the x-axis, also linear. And how much it pulses depends on what your geometric parameters are. Here we have, on the left side, we have alpha is 30 degrees, which means it's moderately inclined. The magnetic field axis is relatively close to the spin axis. On the right, we have alpha is 60 degrees, which means it's almost perpendicular. It's not exactly, okay? And you see that the light curves look different. If you have a very narrow pulsation, the black curve, up here, you get a very intense peak. It tells you, if that's something that looks like that, it tells you that your zeta angle is around 50 degrees. And you might be alpha is 60 degrees or alpha is 30 degrees, but you don't really know. It all depends on structure here. These results were produced by having two antipodal hot polar caps, blue in that diagram, the geometric diagram that I showed you. If you have a perpendicular viewing angle at 90 degrees to the rotation axis, then everything is symmetric. So you get this light blue curve where everything's sort of oscillating around and everything looks like the period's faking. The period is half what it is, what it really is. It's just you're seeing one pole and then half a period later you're seeing the other pole and everything's symmetric. So that's what is producing this characteristic double beat, okay, in the intensity. So the shapes of these pulse profiles then provide probes on alpha and zeta. So that's how we probe geometry. If you have polarization, then you have additional information, same runs, except you're doing linear polarization degree, and it's going between 0 and nearly 100% in these particular cases. But it varies strongly, and it varies out of phase. So when it's high intensity, it has low polarization degree. When it's low intensity, it has high polarization degree. That's a characteristic of scattering. You know, Thompson scattering or Compton scattering in QED. That's actually, it's all part of the physics associated with that. So if you have polarization, you have added diagnostics. But I will note that these were added up, assuming that nothing happened to the polarization in the magnetosphere, that it was just the bare results added up. Okay, so now we're going to go and probe these parameters with examples. Okay, so here is one for a magnetar RXS J1708. And the data actually comes, the data in intensity and polarization comes from the Imaging X-ray Polarimetry Explorer, IXPE. And those are the black dots here. Okay, we've actually excised a few here that have got a problematic bump, which indicate that you have a non-uniformity of surface emission. We're trying to get the best sort of like global picture. Okay, so that means you have to add more parameters if you want to fix the data. Okay, but we get a best fit. So what we have is the normalized rate, in other words, the intensity, and phase in cycles in terms of periods. So that's one period up there, two periods up there. And you see with this data set, models that are symmetric fit it quite well. Okay, some fit better than others. There are different parameters. There are different values of alpha. The alpha are between 55 and 70. The zeta are between 6 and 15 or 14. So that means you're looking almost down the magnetic axis, the spin axis, but the rotator is quite oblique. Alpha is a very large angle. And that's determined by how broad these spins are and what's the ratio between the maximum and the minimum intensity. A bunch of different models can produce similar results, and then we can plot the probability distribution. The probability distribution, black means high probability, pink means low probability, and you sort of see that there are two clusters for a symmetric profile in data, plus, since the models are all symmetric, if you had a symmetric profile in data, these two would be symmetric about the alpha equals zeta line. That's just a mathematical symmetry associated with the geometry of all the different directions. But it's not, because the data are not symmetric. And so we favor this case more than we favor this case. So then you can add up all horizontal cuts in zeta and form an alpha distribution, which is this green one. And you find that you can say, oh, well, alpha is most likely around about 15 degrees or around about 45, 50 degrees. That's what it is. Or you can do cuts, you can add up in the overall the alpha for each particular zeta, and here's the zeta distribution. We had a bunch of different sizes for our polar caps, how broad our polar cap was in magnetic latitude. Theta cap equals 15 degrees is a fairly small polar cap. theta cap equals 35 degrees is quite a big one. And so we can work out what is probable and what is less probable. And we find that roughly around about 15 degrees. That's telling us a physical area on the surface of the star. So we can probe that as well. Okay, we haven't done polarization. Okay, so now we get to the fun stuff, which is how, the last part of my talk. I mentioned that physics goes nutcase when you go to really high magnetic fields. So it was realized in the 1930s by Heisenberg and Euler that there was an effective Lagrangian in QED that for the external electromagnetic field that would force your medium to become dispersive and, in fact, birefringent. And so we call that QED vacuum birefringence, or VB for short. And it's been a fundamental goal and one of the principal goals of IXPE to prove that it exists in nature. Since its strength varies quadratically with the value of the magnetic field strength, it means that the higher the magnetization, the better shot you have at trying to prove it. And so magnetars are your best choice. So what happens is a photon comes in and the Feynman diagram for dispersion in QED has a one loop electron-positron loop, a virtual electron-positron, and you can develop the expressions associated for this for the refractive index. And so with that formalism, you find that with an external magnetic field, as long as the photons are propagating at some angle to the magnetic field, the medium is dispersive. In other words, the photons do not travel exactly at the speed of light. The perturbation is small, but it's still significant. We're talking at the 1% level. Not only does it do that, but the actual dispersion, the speed of propagation of the waves depends on the polarization state. So it's birefringent. Okay, so you have different speeds. So your electric field vector, if it's in a different direction, it will move, the photons will move with different speeds. Moreover, the actual electric field vector will rotate. So it's a QED analog of Faraday rotation associated with plasma dispersion. Okay, it's in the opposite direction because the perturbation to the refractive index is of the opposite sign. Okay, so if this happens, and we believe it does, then we should be able to see the effects of this in what happens in magnetar X-rays. A parallel component to this is the fact that if you take the same diagram and then you pull things around, you're like, okay, well, wait a minute, look at this. How about I cut this in the middle? I cut this, visually in the middle and say, oh, wait a minute, I've got electron-positron pair. How about I make the electron-positron pair real? In other words, I use photons to create electron-positron pair. We call that magnetic pair creation. Both of these were started to be studied in the 1950s. And by the late 1950s and the early 1960s, there were detailed calculations. These two are related because they are part of the dispersion of QED in the magnetized vacuum. This is the real part, and this is the imaginary part. So they're related by the Kramers-Kronig relations, just as with any dispersion. So this process is the fundamental process responsible for pair creation in pulsars, producing radio emission from radio pulsars. Okay, so what does this do? In the magnetosphere, if we propagate photons through the magnetosphere, what happens is that the polarization state that's produced at the surface, if vacuum birefringence is active, it's preserved out to about 30 to 100 stellar radii. So it's imprinted, and what it does is it rotates its plane. It stays in whatever state it is. That means it rotates according to what the plane defined by the photon trajectory and the local magnetic field vector. And that's just geometry of curved photon lines and curved magnetic field lines. And so it sort of freezes everything out in terms of the polarization. The polarization at the surface is sort of 100%. So if it does this, then it's going to freeze the polarization degree at high levels. That's what you're going to look for. If this isn't active, then what happens is the larger you have a patch, if you have emission coming from a whole bunch of different surface regions, they come from different magnetic field orientations, and so their polarization directions of difference. And so they get tangled up in terms of their projection of electric field vectors on the sky. So you tend to depolarize. And ideally, it's just like if you have the whole surface radiating, then you will have a relatively low degree of polarization, which is not what we observe. So that is essentially the difference between the top and the bottom. And the bottom is you have significant polarization degrees at the 20 to 60% level. This is linear polarization degrees up here. But with vacuum birefringence on, you tend to get between 90 and 100%. Okay, so I won't dwell on that. I'll actually go to the results. So we had things get better, and this is the last two slides. Okay, the things get better when you have additional information in a different waveband. So IXPE observed this magnetar 1E1547 minus 54 3 years ago, or 2.5 years ago. And radio observations were obtained at the same time. So we had simultaneous radio and X-ray observations. This is one of a handful of magnetars, there are 6 of them, that actually emit radio waves. So they're a radio pulsar, but they don't do it all the time. So sometimes they're brighter, sometimes they're off, sometimes they're sort of just there. Okay, this was a phase when we had bright radio. So here's the radio. This is the pulse profile of the radio, flux, false phase, and you see it's a very broad radio cone. When you look at the Crab pulsar, it's a very narrow blip. And the Crab pulsar has a very narrow radio cone, and that radio cone is the inclination angle is about 60 to 70 degrees in the Crab pulsar. And so that radio cone is, for most of the pulse period, is not pointing towards us, the observer. But it comes across our line of sight, and it's a very short blip. So it's just a little spike here. And that's typical of radio pulsars that are also gamma ray pulsars. But for this case, it's quite broad. That's 0.25 in phase. And that's a clue that we're coming across a radio pulse cone that is very aligned with the magnetic axis. We also have polarization. And here's the polarization angle or direction of the electric field vector of the photons, the radio photons parked on the plane of the sky. And this can be interpreted with something that was developed in 1969 called the rotating vector model. And you can use it to probe geometric parameters. You put these two together and you find that alpha is 2 degrees and zeta equals 5 degrees, so that you've got an aligned rotator from the radio and that you're looking almost down the magnetic field axis. So that's the radio. Then the X-rays is all this stuff down here. Here's X-ray intensity. The peak is not coincident with the radio, which means it has to come from away from the magnetic axis. So it sort of lags it. Then we have the polarization degree, which is 40 to 80%. Okay, so that's a very high polarization degree. It's higher than any other magnetar with IXPE. So and this is the 2 to 4 keV. We'll worry about the left because those are the what we get from the surface X-rays. Okay, so, and the polarization degree doesn't change much with pulse period, with pulse phase. And then we have the direction of the polarization angle in X-rays. It too varies a bit, but not a whole lot. So then we do an X-ray model, and this points to the question raised earlier, and that is, where does the X-rays come from? Here's the spin axis, and if you try and put the X-rays right associated with the spin axis, then they will be coincident in pulse phase with the radio, because the radio cone is at some altitude, maybe somewhere around 30 to 100 stellar radii above the surface, and we can measure that. We actually estimate that with the radio data alone. And so if they would line up in pulse phase. They don't. The X-ray lags the radio. So the X-ray has to be produced offset, which we believe we chose a wedge. Okay, so the centroid is like about 10 to 11 degrees off the magnetic axis, and we've moved it around so that on the surface, so that it comes into our line of sight at some pulse phase later than the radio. Then we fit the polarization data. Here's the intensity. We fit the intensity with the assimilated wedge hotspot. That's just a preferred simplistic geometry. We can always change that. And then we get the polarization profile as a function of pulse phase compared with the data, which are the black dots. The blue is simulated with vacuum birefringence on. And that means we retain a strong polarization level degree, and we have Stokes Q and Stokes U, and it's always better to do fitting to Stokes Q and Stokes U individually rather than derivative quantities of polarization degree and polarization angle on the sky. If you switch vacuum birefringence off, then you say, okay, I'm going to just sort of try and cancel polarization degrees. Both Stokes Q and U go closer to zero, and they oscillate really wildly because they're picking up oscillations associated with the magnetic geometry as you view it when the pulsar rotates, when the magnetar rotates. And the data do not fit those orange curves. They fit more or less. The statistical quality is admittedly poor, and we're working on that, getting more data to try and improve that. They more or less fit this type of structure. We probably believe it's not a uniform cap here, a wedge-shaped cap. It has a spatial profile across that that's going to distort these curves. We'll worry about that when we get better data, because at this stage, the fits are relatively, they're as good as one can expect with the statistical quality of the data. Yep. Okay. So last point, and that is, so if you then take these plots and plot Q against U, and so that you're not retaining the phase information is in this hysteresis cycle, the blue curves look like the data are the squares, the blue curves look like this with vacuum birefringence on, and the orange ones are offset and don't match the data at all. So the contention is that we have evidence for the action of vacuum birefringence, in other words, different propagations of light speed with different polarizations due to quantum electrodynamics and strong magnetic fields. And that's it. Okay, thanks.
Thank you very much, Matthew. So I'm conscious that it's 3 o'clock, so if people have to leave for other things, please do so. We've got time for a couple of questions before we might move into afternoon tea. So I'll open the floor. Go on, Alexa. Hang on.
No, thank you for a fantastic overview. I just got really intrigued by just seeing the phrase that fast radio burst magnetar connection. Maybe you could comment on what you think about it, because it's really interesting. You have a big view about this.
Okay, that's a whole nother talk is all I can say. So, okay, so another 12 slides. And we have seen from one magnetar, J1935, we have seen fast radio bursts. They were first seen in April 2020. We've seen, I think, something like 5 or 6 at 3 different epochs. And we've seen them in connection with glitching activity. And in one case, we saw them with a double glitch, the first ever double glitch detected from a pulsar. So, and it was detected in X-rays. So there is something weird going on. Not only do we have pulsed radio emission, but we actually have ephemeral fast radio burst. Like the intensity is much less than cosmological fast radio bursts by 5 to 6 orders of magnitude, because they're very near, but they are very bright in terms of radio. So that's what that is. And I'm happy to talk. I can show you some slides. I've got plenty. That's another subject.
All right. Thank you.
Okay.